Okay, time is 2:30, so let's begin here. So project number 4 is due on Friday at noon. Also, test number 2 is coming up. It's April 7th. We will continue chapter 4 today and perhaps start chapter 5. Are there any questions? Okay. We left off in the notes on approximately page 435. So we're talking about now how we can use Poisson regression models to model the counts of a contingency table. And so we have this very simple 2x2 contingency table with the Larry Bird data set. What I would like to do is model these counts, or let's say model the log mean counts as a function of the row variable and the column variable. And so to do this, what we're going to do is assume that these counts here are coming about through independent Poisson distributions. And the first thing that we're going to then do in terms of R is that we're going to enter the data via the array function, like what we did back in section 1.2. Put that into c.table. And then we've converted this kind of data before to a data frame so that we could use it with the GLM function, for example. And one of the main ways that we did that was we used the as.table function and then the as.data.frame function. And when we apply that with the c.table here, this is what we get for our data frame. This is the exact form that we need with the GLM function. We don't need to do anything else with it. And so the freak column is going to be our y. And the first column essentially will be x1. The second column will be x2. And so this is the first model that we're going to fit to this data. So mu here is the expected count for a cell of that contingency table. We're going to say log of mu is equal to our intercept term plus beta 1 times a indicator variable representing the variable first, the row variable, plus beta 2 times indicator variable representing the indicator variable for the column variable, second. Now note that I have first missed there. That's because the indicator variable is a 1 when the free throw is missed, a 0 when it is made. Well, why did R use that? Well, what we've been focusing on in the past is, well, we basically put this in alphabetical order, the different levels. So we have made comes first, missed comes second. So because of that, the indicator variable will be for missed. We got to be very, very careful here. I think there's been an example of this in the notes too. Not the notes, the homework. Because I have entered these levels in that particular order, that's actually how R is determining what is the first level, what is the second level of that factor. If I would have entered the data in a different order here, so that missed was first, made was second, R would have said, okay, the levels for first was missed, made, and the indicator variable would have been a 1 for made. So this is the one place where it can be unexpected to see how R determines the levels of an indicator variable to represent a categorical explanatory variable in a model. Are there any questions about that? Okay. So this model that I had written out here, notice it says that the effect that the first free throw outcome has on the response is not at all affected about what happens on the second, and vice versa. Well, I guess that kind of makes sense to some respect, but think of it, maybe it might be better to think of it this way. Notice the effect that the second free throw attempt on the response is not affected at all by the first. because there's no interaction in the model. So this is actually a model under independence. If I want a model under dependence, well, find the interaction term between these two indicator variables. And then also add a beta 3. So let's first estimate the model under independence. And so, simply, freq tilde first plus second. Here's my data. Family equal, Poisson equal log, just like what we saw with the horseshoe data. Put the results into mod.fit1. And then I get my output. So here's beta hat 0, beta hat 1, and beta hat 2. So that when I write out the model, I would do it as you would largely expect. Any questions? Okay. So, well, what will be then the estimated mean counts? In other words, what does this model say that the mean counts would be for each of those cells in that contingency table if it were to estimate it? So, again, we can use the predict function. And I say object equal mod.fit1. My new data is just simply, well, whatever I had observed previously. And type equal response. And here is the estimated cell counts. So for the 1,1 cell, I estimated to be 252.115. Okay. Now, reviewing some stuff that we learned in section 1.2 and also chapter 3. Back then, we said, well, if I want to know, well, what would this particular cell count be if I had independence? What would I have done? Based upon what you see in these numbers here, how would I have found the estimated expected value under independence? I would take 285 times 299 divided by 338. That's the estimated expected value under independence. And I can actually find these relatively quickly. I'm not for sure if we've done this before or not. I think we have. Remember the chi_sq.test function? I put in my contingency table, correct equal false. And one of the components that's produced by this function is the estimated expected counts. And guess what? These estimated expected counts are exactly the same as what we get from the Poisson model. Because again, it's under independence. Well, how can I estimate then the model that includes the interaction? Well, again, take first colon second there, as we first saw back in chapter 2 for interaction in a model. And this is what I get. So again, beta hat 0, beta hat 1, beta hat 2, and beta hat 3. So this is what the estimated model actually then looks like under dependence. Take a look at the residual deviance. It's approximately 0. Why? Yeah, I have estimated the saturated model here. Notice the degrees of freedom, 0. Well, how is this degrees of freedom found? Observations. Remember, we have 4. Subtract off the number of parameters you're estimating. Well, 1, 2, 3, 4. So the model under dependence here for a 2x2 contingency table structure is a saturated model. So in a saturated model situation, remember what that says. what you predict the response to be should be equal to what was observed. So let's use the predict function again now with this model's fit. And look at this. The mu hats are exactly equal to what was observed. Well, how about we do a test here for that beta 3 parameter? This is going to be a likelihood ratio test for beta 3. Again, beta 3 is for the interaction term, so if it's equal to 0, it says we have independence. So this is a test for independence, actually. So we can use, for example, the capital ANOVA functions we've done many times before. My -2 log lambda statistic is 0.286. P-value is 0.593, so I don't have sufficient evidence to reject independence. You could also use the little ANOVA function too, as we've done many times before. I'll let you look at that on your own. And lastly, let's compare this to a way that we've done in section 1.2 with the isostats function with the contingency table. Notice the test statistic here is exactly the same. P-value is exactly the same as what we just got. So this is just a nice little instructive tool here to show you that you can get the same results as what we had done through simpler methods in the past. Well, what's the advantage of using the Poisson regression model here? Well, for this specific case, there's really not much of an advantage. But if you think of, let's say you had other explanatory variables available to you. Maybe this was, let's say, a 3-dimensional contingency table. So not only do we have Larry Bird's first and second free throw outcome, maybe we have an explanatory variable that represents, I don't know, maybe the quarter of the game. Or, maybe, I don't know, I'm sure there's other explanatory variables you can think of in a basketball context that might be useful here. And if so, or maybe let's say home or away. So, you would think that maybe if you're doing free throws at somebody else's arena, where, behind the basketball hoop, you might have people waving their hands trying to distract you and hope that you missed, perhaps your probability of success would go down versus if it was at home when everyone goes shh and it's really quiet. And so that what the Poisson regression model then allows you to do is easily add those additional components as explanatory variables to the model. So then that gets us into what are called log-linear models. Actually, I guess we could say it gets us into log-linear models. Okay. Now notice the form of our model here. Log of mu, and then we have a linear combination of our betas with our x's. Log linear model. So typically people use this terminology, log linear model, to describe the setting where you have a Poisson regression model and you're modeling counts in a contingency table. So, it's really not anything different from what we're doing. It's just people often use this terminology to describe modeling counts in a contingency table using a Poisson regression model. Also, another aspect to it is that typically in these often in these settings, people write their models in a different way than what we've been doing so far. All of you should have seen an ANOVA model for a completely randomized design before, at least in a Stat 801-like course. If you take a Stat 802, you've looked at a lot more complicated settings involving multifactorial structures. And in those particular settings, let's say you have a 2-factorial model. I'm going to write out the model. So mu sub ij. That's equal to, here's one way that you would write it out, alpha plus beta I plus gamma j, where beta I represents the ith treatment of factor 1, that effect on the mean response. And gamma j represents the jth effect of the jth treatment level of the second factor and its effect on the mean response. And you know, suppose if you have an interaction term, you might have written it like this as well. Does that look familiar? Okay. So since we only have categorical explanatory variables here, we could actually write our model, our log linear model, in an ANOVA kind of format, such as this. And so, for example, this is how Agresti would write this model in his book. Let's say that we have a two-dimensional contingency table, meaning we have rows and columns. Log of mu sub ij, so mu sub ij represents the mean response, row I, column j, is equal to an intercept term, we call it lambda, plus the effect of the ith row representing x, the x variable. So that x in the superscript there is not saying you're taking lambda to a power. It's just a notational device that people use to say, okay, this is the lambda, this is a parameter that shows us the effect of the ith row corresponding to x on the log mean response. Then for the column response, you could do something similarly and say lambda jy. So that would be a model under independence, because notice we do not have any kind of interaction term represented there. The model under dependence would be written a similar way, where now we also have lambda ij with a superscript xy. All those lambdas are parameters that you would want to estimate. Now, for those of you who remember this, hopefully it's all of you, if you did have a 2 factorial model such as this, at least you've seen a 1 factor model in a Stat 801 class. All of you should have seen that. But if you had a 2 factorial model like this, can you estimate all the betas and all the gammas, all the beta gammas? Can you estimate them all? Or do you have to make some kind of simplifying assumption? Ever heard of estimability problems? I know in Stat 970, I know some of you have taken that course, you should be talking about this. Do you ever have constraints on these parameters? These are all fixed. Don't worry about random effects. I might have to talk to Walt Stroop, who's teaching Stat 970 to some of you right now, and say, hey, I think some students are not getting what they're supposed to. For those of you who've already taken it, I hope he doesn't go back and change your grades. Of course, I'm just joking. Anyway, perhaps this sounds familiar. You could say all these betas sum to 0. Or you could say, how about we set one of the betas equal to 0 and then estimate the other betas? Does that sound familiar at all? Okay, so we're going to do the same thing here. So we would set, what R would do is set the first level equal to 0 for the lambda x and for the lambda y. And then in terms of the interaction terms, what ends up happening is that only the last level is something that you can estimate. Okay. Now, again, this is just a different way to write the same exact model that we had just written, at least in estimated form, for the bird data. Same exact model. And so, this is what we had with the bird data, the estimated model. Now, using this alternative ANOVA-like format, instead you would write the model like this. Mu hat sub ij, here's my intercept term. And then we say plus lambda 2x hat plus lambda, oops, I actually don't have it exactly the way I want it. Excuse me. Let me change that. Change this to I and this j, and you would say lambda hat I, lambda hat 1, 0, not right. Let me start again. That's how you would write your model. So if I want to know, well, what's the estimated mean response for row 1, column 1, how would you write it? Mu hat 1, 1 is equal to E raised to what? 5.53 plus 0. Because remember, lambda 1 for the x and the y are set equal to 0. But notice that this is essentially exactly the same as we did here. Let's again think of the first observation, which would be row 1, column 1, based upon how we estimate it. Mu hat is equal to exp 5.53 minus 1.68 times what? 0. Minus 2.04 times 0. Exactly the same. And so hopefully you understood this, and your instructor emphasized this when you took a Stat 801-like course. ANOVA is equivalent to regression. ANOVA is actually just a special case of regression models where you have categorical explanatory variables. This is a perfect illustration of that. Sometimes that point can be lost when you're taking a course or those kinds of courses. Hopefully it's not lost this time. And to be honest, I don't really see why there's a big deal to differentiate between the two. So I don't, because the models are the same. If this course was offered about 20 years ago, which it was about a little bit less than 20 years ago for me when I first took it, we would spend about 6 or so class periods talking about how to analyze the counts, how to analyze the counts of contingency tables using log-linear models. And then we would also have a separate section on Poisson regression and talk about, now you have maybe a continuous explanatory variable with maybe also some categorical ones mixed in. Nowadays I don't really think it's really worthwhile to make that distinction. All of it's essentially just the same. Any questions? So let's talk about larger log-linear models than just simply for a two-dimensional table. So we talked about with respect to the bird data, you could have, essentially, well, what quarter of the game bird has to shoot the free throw. There are 4 quarters, so there will be 4 levels for that, let's say maybe a third dimension to a contingency table. For a fourth dimension of a contingency table, you could also have, is it a home or away free throw attempt? And so you could have a 4-dimensional contingency table, and you would want to model that in terms of a log-linear model structure. I get a little bit more into the log-linear model-like structure in my book than I do in our class, because I'm afraid that some readers are used to, if they have had some of this stuff before, they're used to really spending a lot of time on log-linear models. And so I do talk about a little bit more detail. Please take a look at it. But really, again, there doesn't need to be that distinction. Was there a question?
Yeah, the previous discussion. What do you call that? What's the name for that? When you set the parameter to 0?
A set equal to 0 constraint.
Is there a name? Is it some kind of coding?
I'm sorry. Let's actually go back. Just to make sure I know what you're talking about. Did I skip it? I think I did. Sorry. Right there. Right? Okay. So you could just simply set one level equal to 0 and then estimate all the other parameters that you would have available. So imagine a setting where not just a 2 by 2 table, suppose this may be 10 by 10. So you would set lambda 1x to be equal to 0, and then estimate the other 9 lambda x's. That's equivalent to using indicator variables in a regression model. Because you have the base level, so essentially you're saying, in this particular case, you're saying that first level is the base level, and then you estimate, let's say, betas for the other 9 indicator variables. Exactly the same. Does that help?
Yeah. Is it the same as centering, or is it the same?
Centering,
Yeah.
in terms of like what you might do with standardization, then the answer is no. Like if you're in some regression settings, you might want to take xi minus x bar. It's totally different. So anyway, so there's a 3-dimensional contingency table to show you what one would look like. And again, just write out, the model in terms of a regression setting, or if you want to in an ANOVA-like setting, include various interactions as needed, and you can use it. Okay. So then I think what this does, it leads us to a good discussion of, we've talked about in this class in a few different instances about how to do how to do some kind of analysis for a data set, maybe 2 or 3 different ways. In particular, here we can analyze the counts of a contingency table through using an underlying Poisson assumption. So each count is essentially independent Poisson with a particular mean. Or we could say that all the counts come from one multinomial. Or in fact, if it was just a 2-dimensional table, you can think of it as each row has one multinomial. So there's a variety of different ways. And in the end, you will actually get the same result. In terms of the models will be equivalent, likelihood ratio tests will be equivalent, and so on. Well, why does that occur? Here's why. The joint probability distribution of ij independent Poisson random variables. So what do I mean by joint probability? Well, in your very first stat course, you talked about the probability some event A intersect B. That probability, well, that was a joint probability for the events A and B. Okay, so in this case, the joint probability distribution of ij independent Poisson random variables, which means since essentially all you would have to do is find the Poisson distribution for 1, 2, 3, and so on random variables and just multiply them together. If you take that, but you condition on their overall sum, so just add up all your counts, condition on whatever that sum is. So, again, in your first stat course, you talked about conditional probabilities, such as probability A given B. That's what I'm talking about. Then this new distribution is a multinomial. Now, for those of you who've taken Stat 882, you should be able to prove this. Master's Comp exam in August. I have to submit a question. What should I submit? Let's talk about how you would prove it. For this class, what are you responsible for? To understand the fact that we have this relationship between a Poisson and multinomial, and the fact that whatever way you approach it, you're going to get the same answer. But what I'm going to show next you're not responsible for and that is the proof. Okay, it's actually not that difficult. So let's say that my counts in a 2 by 2 contingency table are denoted symbolically exactly the same way as they were in chapter 3 with n's. These n's are random variables, And let's say that each of these n's has an independent Poisson distribution with a mean of mu sub ij. Okay? So if they are independent, that means if I want to find the joint probability distribution, let's call it f, for these 4 random variables, I just simply multiply all the Poissons together. Everyone with me so far? Any questions? Okay, silence means you completely understand this and you don't want me to go on because you could do it right now. So let's simplify. Well, I got this e raised to the negative mu sub ij there. Well, what I can do, since it's still e for every single term, I can just sum up what's in the power, and then I'm left with, again, the stuff that's in the product. Okay. Let's let n plus plus be the sum of these n's. I could have just called it n. I decided to call it n plus plus. Well, again, in the Stat 882 class, you would learn that the sum of Poisson random variables is Poisson. In fact, you could prove it with a moment generating function technique very easily. Maybe that's an MS Comp question too. So you could prove that, and what I did was at the very beginning of this section, I stated it. So again, don't worry about it. And so the conditional distribution then, where I take my random variables again, condition on whatever that sum is, ends up being, well, the joint distribution divided by the distribution of just n plus plus. So from there then, you can write it out, do some simplifications. I'll leave the details up to you. And look at the very end here. Look how this is looking like a multinomial distribution. You have this n plus plus factorial, and you divide by the product of a whole bunch of random variables, or the observed values of the random variables, where you're taking the factorial of them. And then I take the product of mu sub ij divided by the sum of all the mu's raised to the n sub ij power. Well, how about I just call this guy here pi sub ij. And now that should look just like a multinomial distribution that we saw towards the beginning of chapter 3. That's the proof. My bird_chapter4.r program contains some additional code to help demonstrate the equivalences of the two. So I look at it from a multinomial standpoint, and I looked at it from a Poisson standpoint to show that indeed you do get the same results from stuff. So you might be wondering, okay, so I have more than one way to do exactly the same thing. Which is better to use? There's not just, in many situations, there's not necessarily one best way. But here's one way to think about, well, do I want to work with a Poisson or do I want to work with a multinomial? So, I guess starting from here, you are now responsible for all the material. So it depends upon how you view your data and the form that the data comes in. With a Poisson setting, notice what we're doing. We're taking the log of the mean response is equal to all your variables of interest. So essentially here, you could, even though that those variables are on, let's say, the right-hand side of the model, you can kind of think of those as responses. All the stuff that will be on the right side would be responses. Response variables, that is. Where with a multinomial setting, notice you have to pick one response variable. Like with the fiber data. We had to pick, well, it makes sense. It has to be the bloating response. It wouldn't make sense to think of the type of cracker that a person is given as a response. We're looking at, well, how does the cracker affect bloating? Where with the bird data, you can kind of think of, okay, what happens on that first attempt, that's kind of a response. What happens on that second attempt, that's also kind of a response. So maybe a Poisson model might be the better way to approach it than a multinomial setting. So that's what it essentially comes down to. Now, since we are talking about contingency tables here, as you might expect, odds ratios can be very useful. So this is the one place where odds ratios for a Poisson regression model can be very useful. So what do I mean? Well, estimate a model, get the estimated mean counts out. Use those mean counts to form odds ratios to interpret the model's fit. Okay. Now, also something that you can do with these kinds of models is that, and we saw this a little bit with the multinomial, with the proportional odds regression models, is that you can also have ordinal categorical variables. And you can include those in a Poisson regression model setting. I typically skip this, because I don't think it's really too difficult to figure out how to do it. You're welcome to take a look at section 4.2.6 in my book, which explains it in more detail. But I'm not going to ask you a question directly on that. Okay. Are there any questions before we move on to the next section? Okay, so this is section 4.3, Poisson regression models. Okay. Now, oftentimes, when you observe a count response, you have to take into account the exposure length. What I mean by that is, let's say you go to Lincoln's Airport here, and for an hour you watch the number of planes that arrive, that land. Okay? And so then after that, maybe you go home. And then the next day, maybe you have 2 hours to do this. You watch the number of planes arrive, and then you go home. And maybe the next day, you have 8 hours. So you just sit outside the Lincoln Airport for some reason, and you watch the planes arrive, and you count the number of planes. Now think of that now in a Poisson setting. You know, that count is probably going to be affected by, essentially, the exposure time, how long you were sitting outside watching the planes land. You need to take that into account then in your Poisson regression model. But the exposure time itself is not necessarily something, is not an explanatory variable. All it is just because how you observe the data, you need to take that into account. So in those settings then, we have what's called Poisson rate regression models that can be used, where that rate there is what I'm talking about for that exposure time. So some other examples then. The number of times a computer crashes during unequal time periods. The number of melanoma cases per city size. So notice in this case, this isn't a time, but you would expect Omaha to have a lower number of melanoma cases than New York City, solely because New York City has such a greater population. And you need to take that into account in your analysis, but it's not an explanatory variable. So the way that you do that is, instead of just analyzing y, the count itself, let's build a model for y divided by t, where t is this exposure measure, this rate measure. I often refer to it as a time period or baseline measure. So in the Lincoln Airport example, t would be, let's say, 1 for 1 hour. T would be 2 for 2 hours. T would be 8 for 8 hours. That's what you're going to try to model. And try to model the expected value of y divided by t as a function of explanatory variables, instead of just expected value of y itself. So this is what our model then looks like. Now t is a constant. This is not a random variable at all. And we would model it like this. The log of mu divided by t. So expected value of y divided by t is mu divided by t. It's equal to beta 0 plus beta 1 times x if we only have one explanatory variable. Well, using properties of logs, look what happens. That log of mu divided by t becomes log of mu minus log of t. Okay. How about we move this minus log of t over to the right-hand side? We can do that. So now we have just log of mu, is equal to beta 0 plus beta 1 times x plus log of t. This log of t there, notice it doesn't have a beta in front of it. So we are not estimating a corresponding parameter for it. Also, this log of t has a special name. Whenever you see something on the right-hand side of a model such as this, where there's no parameter in front of it, that's called an offset. Again, that's called an offset. Look at the effect that this offset has on our mean response, though. So mu, then, is equal to e raised to the beta 0 plus beta 1 times x plus log of t power. Again, using properties of logarithms, that log of t then becomes just a t out there. So what happens is we're taking our what we would have normally had for our mean response, and we multiply it by t, the length of exposure. Which makes sense. You know, if I watch planes for 1 hour or 2 hours, well, I'm going to have a different mean response. So let's just simply make that adjustment. If one wanted to actually emphasize, you know, your ith observation, notice how I put an I here, and I put an I there. Because every observation or data set could have a different exposure time, exposure length, however you want to put it, a different t. So how do we estimate this model? How do we do inference from the model? How do we interpret the model? Well, just do it the same way as we've done with Poisson regression models before, taking into account the fact now there's a t you have to worry about. So let's take a look at an example. So we're going to go back to horseshoe crabs and satellites again. Now this data is not a rate data problem, or rate data data set. But what I'm going to do is convert it to a rate data set so that you can better compare, let's say, the record version of a data and the rate data. So this is more done for demonstration purposes rather than what I would actually do in practice. So let's let y now be the number of satellites for a distinct width. So before we just said y is the number of satellites. Now we're going to say y is the number of satellites per distinct width that we have available to us. T is going to be the number of female crabs per distinct width. So for example, if you look throughout the data set, you will note that there are 3 crabs that have a width of 22.9. So T will be 3. And if you look at what was originally the response that we had for those 3 crabs, one had 4 satellites, one had 0 satellites, another had 0 satellites. Add them up, now my response is 4. 4 plus 0 plus 0. That's what I'm going to be modeling now. So just to emphasize the point, sometimes it's not necessarily totally clear the first time you see it, the top table there is my original data. That's what it looked like. Every observation was 1 female crab. The bottom table here is my rate data format of this data set. And so basically what I'm doing is I'm going to aggregate my data over the same widths. So for a width of 22.5, there were 3 crabs, 5 satellites. And in the example that we already did, 22.9 in width, there were 3 crabs, 4 satellites total. Is everyone comfortable with this data format? Okay. So how could I do this aggregation in R? Well, since I use the word aggregation, as you might expect, we could use the aggregate function, which we've actually started using back in chapter 2. So I say aggregate formula equal satellite tilde width, and I want to sum up all the number of satellites. That will give me my new version of y. Now if I do exactly the same code with length, that's going to count the number of crabs per unique width. So this is going to give me my t. And again, from doing that, I get my new version of my data set. Okay. So let's estimate the model. So again, you use the GLM function. I'm going to say formula equal satellite tilde width. Nothing new there. And here's the new part. Offset. Remember, I'm going to have log of t on the right-hand side of my model. So I say offset log of the number of crabs. That offset's the key. It's an actual function R that when used in a formula argument like this, it tells R, hey, don't estimate a beta for this term on this right-hand side of the model. Then I just specify where my data is, family equal Poisson, link equal log. And so if I estimate it, here's my output. Let me actually go over here to Word so I can mark on the output. So here's my beta hat 0, here's my beta hat 1, and guess what? The beta hat 0 and beta hat 1 were exactly the same as what we had earlier in the notes. The difference in how I write my model is that now I say plus log of t. Look what happens when log is 1. I'm sorry, look what happens when t is equal to 1. Log of 1 is 0. Then your model is exactly what we had essentially before. So what this log of t is doing is helping us account for that. Well, now each observation might represent multiple female crabs. So when that is happening, I want to get then the predicted mu for that particular setting. I can make the change, or I can make the adjustment corresponding to what t is. So how do I find the estimated value of mu? Well, I use again the predict function. For new data, I say data.frame with, let's say I want to predict at 23, but now I need to also include my t. So I say, how about if I try 1 crab? Or maybe I might want 2 crabs. So I'm going to look at 23 there. And here's what I get. And as you might expect, the 1.59, if you take it times 2, you get 3.19. So it's not too difficult. Well, how about we look at a graph of the model? So I'm going to actually skip ahead to the actual graph itself. Now this can be a little bit more difficult to look at a graph of the model because you have to take into account t. And so on the on the x-axis I have width. My y-axis I have the number of satellites per distinct width. And the plotting character corresponds to what t was. The lines then correspond to the model for the for let's say t equal 1, for what t equal 2 give you, t equal 3 would give you, and so on. The corresponding mu hats. The lines you notice there are not the same length. I drew the lines from the minimum for a particular value of t to the maximum. So if we take a look at when t is equal to 1, I'm sorry if I didn't say this correctly. So there was one female crab that had a width of about 33.5. There was 2 crabs who had a total about 15 satellites that had a width of 29.25 maybe. Let's take a look at the lines. So this black line is for t equal 1. And essentially what that line is trying to do is trying to go through kind of the middle of those ones. You know, think of what a regular old a normal linear regression model does. It tries to go through the middle of your observations. If you do a scatter plot of y versus x, it's essentially what's happening here. Then when t is equal to 2, this red line is trying to kind of go through the middle of those points that are labeled with 2's. And so anyway, so you can look at the other colors. The color, so green corresponds to 3, blue corresponds to light blue is 5, dark blue is 4, and so on.
So we are modeling all the weights separately.
I wouldn't say separately. I mean, you're doing it all at once. It's just I'm graphing them separately, since our response itself is dependent upon t. So for every t, we essentially have a different mu hat as a function of width. And so that's a graph of the model there. Kind of interesting to look at. I want you to take a look at the code for how to do this plot on your own, but I do want to make a few notes to help you out. I had to find the number of unique values of t that were in my data set. So the way that I did that was use the table function, which we've done before. Now when you do the table function, you'll notice that there are labels given to you in the output at the very top of the output that tells you, okay, this is for category 1, this is for category 2, this is for category 3, and so on. To extract those, then I use the names function. And then to convert it to a number, rather than by default would be like quote 1, end quote, quote 2, end quote, I use the as.numeric function. Again, this is one of these places where in R, what you can do to see what happens, you first execute just this part, then you execute this part, and then lastly you execute this part to see what R does. That's a great way to learn. Then to do the plot of my data, because I needed to be very specific about how I draw the points itself, I use the type equal n argument value there. And what type equal n means, don't actually plot anything except for set up the y-axis and the x-axis. Do not plot any of the data. The reason being, notice how the data has a different symbol for each, has a different symbol depending upon what t is. And so what I did was, as we saw in chapter 1, I used a for loop, where now in the points argument here, the points function, I drew the actual values of y versus x, where the symbol that's actually being used corresponds to t. So it is kind of a complicated plot, but again, step through it, and you'll be able to figure it out. Okay. So, as I said, the Poisson regression model that we got previously was the same as the Poisson rate regression model that we got now. There are some small differences in terms of, if you look at the residual deviances for the two models, they are different. Why do you think that occurs? Maybe think about, well, what does a residual deviance do? It's a likelihood ratio test that compares what two models? The saturated model to the model, let's say, under investigation, you could say. Because our data is in different formats, the definition of what a saturated model is different. One way to think about it is, okay, well, how many rows are in my data frame for the regular Poisson regression model versus now this Poisson rate regression model? Well, with the rate regression model, remember, we had to aggregate my data. So if I had to aggregate my data, I have less rows. So I'm going to have less degrees of freedom overall. And so it makes sense that, yeah, my -2 log lambda statistic, my residual deviance is going to be different. So that's why that happens. That's actually not that important, though, to be honest, that this happens, because let's say that I want to do a hypothesis test for width, which makes sense. I want to know, is width important or not? What ends up happening is my negative 2 log lambda statistic that I get for testing just width itself. Of course, I'm going to only have 1 degree of freedom with that because I still have 1 beta. The negative 2 log lambda is exactly the same, no matter if I use Poisson regression or Poisson rate regression. So that's why it's not a big deal that the residual deviance itself is different. Where it can matter some, the differences there is in chapter 5 when we try to evaluate the overall goodness of fit of our model in terms of how good is our model. Then this can matter some, and we'll address that in chapter 5. Do note that if you remember with the place kicking data set, we looked at it when we just had distance itself as an explanatory variable. We looked at both a Bernoulli format and a binomial format our data. The residual deviances of those two models will be different, just like what we had here. The key, though, is if I were to test the importance of distance, I'll get exactly the same negative 2 log lambda. Okay, so that takes us to section 4.4. Zero inflation. You're not responsible for this section, but I do at least want to point it out to you to give you a little bit of a background of what does this mean. Well, with Poisson regression models, I think more so than, let's say, logistic regression models, there are some issues that you often run into. In particular, with Poisson regression models in section 5.3, we're going to talk about something called over-dispersion, meaning that the variability in your responses is more than what you would expect if truly a Poisson distribution held. But another thing that can happen when you're working with Poisson regression models is something called zero inflation. And that simply means is that you observe more zeros than what you would expect if the Poisson distribution was correct. So how do you account for that? And again, this can happen in actual application. The way that you can account for it is actually to use what's called a mixture distribution. Not just Poisson, but a mixture distribution. If you've never heard of that, that basically means you're basically using two distributions at the same time to some respect. So, excuse me. So what you would do is assume that y has a Poisson distribution, like normal, but not all the time. Y doesn't have a Poisson distribution all the time. It has a Poisson distribution with a probability of 1 minus pi, where pi is like that Bernoulli success probability that we first saw in section 1.1. When y is equal to 0, you don't have a Poisson distribution anymore, you say. And the probability of y being equal to 0 is your Bernoulli success probability. You can use that then to set up a likelihood function and then to do your modeling. In particular, you can set this mu to be a function of explanatory variables, just like what we've done before, and you can set this pi to be a set of explanatory variables, just like what we did before. And both don't have to be exactly the same sets of explanatory variables. So it's kind of cool. If you want to know more information about it, see my book. I do believe that if you take Stat 971, you do spend some time on zero inflation. Does that sound right for those of you who've taken it? Yeah. Okay, so that concludes chapter 4. Okay, so let's go into chapter 5. This is the second longest chapter in my book. So it's going to take us some time to get through. I'm not for sure if we will have a project corresponding to it. So, please take note of that, and that you might want to take extra time to go through the book, to go through my notes. Again, I expect you to reproduce all the examples that we talk about in class. I expect you to do that. So you might want to take some extra time for it. It's just, I still have to give you the project corresponding to Chapter 4, which it is written. I anticipate giving it to you after you turn in your projects, your project that you're working on right now. And the problem is, in terms of the time where we are in the semester, sometimes it's just hard to fit in another project. So Chapter 5 says, okay, we spent chapters 1, well, let's actually talk about, not 1, but chapters 2, 3, and 4, talking about how we can use essentially regression models to model various kinds of categorical responses. But we haven't spent any time talking about, well, how do we evaluate if a particular model is good or not? How do we choose between one model versus another model? How can we evaluate, well, maybe the model works well except for a few observations where the model just doesn't fit very well. And so in this chapter, then, we're going to talk about model selection and evaluation. We want to determine the most parsimonious model that best estimates the response, meaning that we want the smallest number of terms or the smallest number of explanatory variables in our model, but yet gives a very, very good estimate of our response. And then we'll also talk about how to assess how well the model fits the data. So let's talk about variable selection. So there's going to be 3 situations we're going to talk about, where we're going to focus on the third one. So the first one, in some situations, you will have a specified number of explanatory variables, and you need to include them all in the model. For example, taking Stat 802, you talk about experimental design. You have a designed experiment where you have, let's say, maybe 3 factors. Well, you're going to have to include variables that represent all 3 factors in your model. Okay, so in that particular case, you cannot necessarily select, well, which variables do I include? You need to include them all. Situation 2, especially if you are a non-stat major, based upon your background, you might think a particular variable is important. It's going to affect the response. And even though if you do a likelihood ratio test, you can include that the p-value is large, it's non-significant, you're still going to keep that variable in the model. Because based upon your background, based upon maybe what other people have concluded, you need to include that in that model. What we're going to focus on, so in that particular case, variable selection isn't important. So you're going to keep a variable in the model no matter what. We're going to focus on number 3 here. So imagine a setting where you have a number of explanatory variables. You don't really know which ones to include in a model. So like with the place-kicking data set, I had a number of variables. I didn't know which ones to include in the model to begin with. So for example, in many observational studies, this occurs, such as with the place-kicking data. So because of that, you would like to only include those explanatory variables that will truly help you predict the response. So you need to do variable selection. You need to figure out which variables to include in your model and what form should they be in the model. Should there be an interaction between 2 variables? Should there be a quadratic term? Maybe some other kind of transformation. You need to figure that out. That's what we're going to be focused on here in section 5.1. Also, for the whole chapter 5, This is where if you would have a whole course on regression analysis, it's like Stat 870, this is where it will be most important. We're going to be essentially doing exactly the same thing as what you would do in Stat 870, except for more fancy models. Than in Stat 870, you would only look at y is distributed with a normal distribution. Okay? So, but I will approach this from the point of view of understand that a lot of you haven't taken a course like Stat 870. So I'm going to find a happy in-between point between if you had or if you hadn't. If any of you would like to see how one would actually approach this in the Stat 870 setting, please take a look at my corresponding lecture notes and class videos that are online. When I taught Stat 870 last, focus on chapters 7 through 10. Okay. So we're going to talk about something called information criteria. And the build-up to this is that, you know, we need some way to compare two models, or equivalently to decide, should this variable be in my model or not? We need some way to do that. Of course, we've done, you know, some likelihood ratio tests before that test the significance of a particular variable. So you might be thinking, yeah, you could use that. We've also looked at, of course, a likelihood function too. Well, before I get to a likelihood function, let me backtrack a little bit. So when we talked about a likelihood ratio test, you know, one of the things that you needed was that your null hypothesis model was nested within the alternative hypothesis model. In other words, that null hypothesis model had to be a special case of the alternative to get the corresponding betas to be equal to 0 in the null hypothesis. So that is somewhat limiting then. And also, hypothesis tests were not designed to do repeated tests to select variables. Even though they're often used in that manner, they're not necessarily really designed for that. You know, in the simplest way to think about it, look at how you could propagate errors as you do successive tests of variables or corresponding parameters. Because, you know, each test has a particular error rate. So instead, you might think, oh, well, how about we just look at the residual deviance? Because after all, that's a measure of how well your model fits versus a saturated model. Ideally, we would like a model to have as low of a residual deviance as possible. Because that means with a lot smaller number of variables, hopefully, or a lot smaller number of parameters, you are still approaching basically what your observed data is telling you. Or you might think, well, how about you use the likelihood function? Because you know, when we first started talking about maximum likelihood estimation, the higher that likelihood function, the more reasonable a set of parameter values were. So you might be thinking, okay, maybe overall, if my likelihood function keeps on going up, 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 my model's better, better, better. The problem with that is the same as what you hopefully have learned in another class, is when looking at R squared. What's another name for R squared? Coefficient of determination, exactly. Now, at least in Stat 801, all of you should have seen R squared, and what was that used for? To measure the overall fit of the model. And so, R squared was between what two numbers? 0 and 1. The higher R squared, what does it say about the model? The better the model. Okay. Now, hopefully, you learned this, but you may not have, depending upon if you've what you had in 801 or if you've taken another regression course. If I keep on adding variables to my model, even if they're nonsense variables that don't make sense, what happens to R squared? It continues to go up. So if you're trying to compare two different models where one has a lot more variables than another, this model has a lot more variable, is going to have a higher R squared than this one. So that's a problem with R squared. That same kind of problem then occurs with using likelihood function, with looking at the likelihood function in terms of the higher the better, or looking at the residual deviance, the lower the better. The same kinds of problem occurs. So then, what's better to use are these things called information criteria. And what this is basically you look at the likelihood function. And again, the larger the likelihood function, the better, you would say. But you also attach a penalty to it for having too many variables. That way, it counteracts adding nonsense variables. So, what was the fix to the r squared that the adjusted r squared? Well, this is kind of like it's not exactly. It's kind of like an adjusted r squared. And this is what the information criteria looks like. It's going to be a function of k. So that k is going to be our penalty that we're going to assess for continuing to add variables to our model. You're going to take -2 log the likelihood function evaluated at the parameter estimates plus your penalty, which will be some positive number, times the number of parameters that are in your model. Let's just call that r, for the lack of a better way to represent it. Okay, so if the likelihood function keeps on going up, that says your model's better, right? So what happens in the log likelihood function? Is it higher the better or lower the better? If you take the log of the likelihood function. For those of you who know your math, it's a monotone transformation. So that means the higher the better still. How if you take 2 times the log likelihood function? The higher the better. Now if you take -2 times the log likelihood function, the lower the better. So the lower that this information criteria is, the better the model is. Now remember, we have this penalty here, and we are adding the penalty. So look what happens there. As my number of variables go up, my information criteria goes up too. And so instead of then my information criteria always going down as I'm adding variables to my model, it will get to a point where it say, oh, you've added too much, and your information criteria won't go down anymore. The key is the lower the information criteria, the better the model. Very simple. On a test, I could ask you a short answer question and ask you to explain to me why is it the lower the better. And so you go through a similar discussion as what we just did. Here are 3 different information criteria that we're going to look at in this class. They all differ based upon what they use for the penalty. In other words, what do they use for k? The first one is Keki's information criteria. Sometimes people will pronounce this as, it's Japanese, akayeki, something like that. Anyway, most people will still pronounce that keiki, even though it's a mispronunciation. I'll just call it the AIC. That way I get around it. So simply, just use k equal 2. Okay. There's also something called a corrected AIC. This correction came about to account for maybe some sample size issues, for example. So notice that penalty there, 2 times n divided by n minus r minus 1. Or equivalently, take AIC plus this constant. You can work out the math and it ends up being that way. That's the corrected AIC. This corrected AIC actually came about, though, through looking at normal linear regression models. So while we are not looking at normal linear regression models, we will still apply it here. It's just some of the theoretical justification for it wasn't actually developed for our particular case. And lastly, there is the BIC, the Bayesian information criterion, which uses k equal log of n as the penalty. Justification for why doing this came out, or really became prevalent, starting about 10 years ago. And so, when I was in grad school, we didn't necessarily really focus on using information criterion. We actually did hypothesis tests, typically. to make a decision about which variables to include in a model. But if you're interested in knowing more about why to do this and justification for the form of the these penalties, take a look at that particular paper there. Unfortunately, we are out of time. Are there any questions? Okay, have a good spring break. Again, the project is due tomorrow.